Okay, so last time we worked, we got this graph here, and we we saw that we were doing the variable a1, and we conditioned it on river size, which was a categorical variable or nominal variable that had three possible levels, and so we could see the distribution of a1 given that river size is small, distribution of A1 given that river size is medium, and so on. For the next results, we're going to need the library HMSI, which is here. If we check here, load packages, I think I have it in here, but you may need to download it first and load it in. And now we're going to try the same kind of thing, but we're going to be using, we're going to condition on two different variables, and in fact one of the variables will not even be initially categorical or nominal. And we're going to be working with this variable from the algae set MnO2, and we're going to use this function called equal count, and we're going to do this thing called overlapping. And this is a kind of when we're creating, when we're working with a first of all, this variable here is a numerical variable, and it's a continuous variable. And so if we want, and this is going to be one of the variables that we're going to condition on, and so in order to do that, we need to make this variable into a discrete variable, or like a categorical variable actually. So we need to break up the values into bins. And this is a kind of unusual approach to this because we're allowing overlapping of the bins. And I think this is called fuzzy discretization. So if you want to look up some information on that on the internet, you can. It's a kind of unusual approach, but a kind of modern approach to binning of or discretizing a continuous random variable, continuous variable. Let's just make sure that let's check the MnO2 variable. So I typed in head algae here and MnO2 here. We can see that it is a continuous variable. What we're trying to get is the following. We are trying to produce this graph, and here we're using MnO2. We remember that it was a continuous variable, but we've broken it up into pieces, and so here's like one piece, here's another piece, here's another piece, here's another piece, and so we're saying, like, given this set of values for MnO2, what does the variable A3 look like in regard to winter, summer, spring, and autumn? So we're conditioning actually on two variables. We're looking at A3 conditioned on this MnO2 and on winter, summer, spring, autumn, or the season variable. And MnO2 has been discretized into basically four bins. So looking at the way we discretized this algae $MnO2 variable, we use this function. We use the equal count function. So let's take a quick look at that. So let's type in this command, and that brings up this page. And this is part of a class called shingles in the lattice package. So we'll just take a quick look at this. A shingle is a data structure used in Trellis, which is a package, and is a generalization of factors to continuous variables. So remember that factors are for nominal variables, but it's a way of making continuous variables into factors. So in order to do that, you just have to break up the continuous variable into sections, basically. So it consists of a numeric vector along with some possibly overlapping intervals. These intervals are the levels of the shingle. Okay, now if we go here, it says equal count converts converts x to a shingle using the equal count algorithm. This is essentially a wrapper around the co-interval. So let's check this co-interval. When it says that it's a wrapper, basically it means that it's just this function co-intervals, and then with a few added features in it as well. So let's look at the co-intervals. So let's look at this. And this is the co-intervals. And here we see an example of using the co-intervals. And we see that there's something called overlap. We also see that there's an input, which is a vector x. So that's where we'll input our variable, MNO, whatever it was. And there's also an indication for the number of bins that we want. So here, down here, we can see that number is an integer, the number of conditioning intervals. And here is the overlap, and it should be a number less than 1, and it could be 0. So if you have 0, that's kind of standard way of binning a variable, but you can have some overlap as well, so that you get this fuzzy discretization. So now going back to the code again, we see that we're using equal count. We're going to create 4 categories. We're going to take this continuous variable and break it up into 4 categories, and we're going to allow for a little bit of overlap as well. 1/5. We're also doing this, which is kind of cleaning up the data. We're saying take out the non-available rows. If we want to see what this new variable looks like, we can type it in and do this. And we see that it gives us, first of all, the original data. This is our original data for this variable. But now it's broken it up into 4 categories. And basically, it takes the values from 1.4, which presumably is the smallest value in the data set. I don't know where that would be, but presumably that's the smallest value in the data set. And the first interval goes up to 8.2. And the next one begins at 7.5. So you can see there's a little overlap here. And goes up to here. And this goes from up to 9.9. And then this one starts below 9.9 at 9.6. Goes up to 10. This one starts below 10.8. And goes up to the presumably the highest value. And then we just get the count for each of these intervals. And that's what we mean by binning. But it's just we're allowing for some overlap. So if you, if you want to look up why you might want to do this overlapping, you might look up fuzzy discretization. So now we've discretized our continuous variable MnO2, and now we want to make a plot. And then we're going to call this graphics function strip plot. And this also comes from the lattice package. And this is going to generate the graph that we saw here. So we have MnO2, this is one of the categories of MnO2. I think this is the first one. This is the second one. This is the third one, and this is the fourth one. No, I'm sorry, this is the first one. The bottom left is the first one. So that's the lowest values of MnO2 are there. And then the next lowest is here, then here, then here. So what comes here to the left side of this tilde this is called a tilde. To the left side of that will appear as the strips here. So here's a strip, a strip, a strip, a strip. And what appears here is the variable that we're looking at. So that's A3. And then we're also conditioning according to this other variable, this other nominal variable that we created from the continuous variable. Okay, so this is the final code that we use to generate that graph.